Okay, to make this video as quick as possible, I'm going to just get straight into the questions. So if you are having algebra issues or other reasons why you're getting the questions wrong, you're going to need to watch and listen carefully or rewind and try and understand where the math might be going wrong for you versus the formulas or the problem solving. So very quickly, let's get straight into the first one. I'm also going to do only one version of the quiz, so this may not give you the exact answer of your quiz. What it will do, though, is go over how to do the math. The very first thing I told everybody to do is please make sure that you're pulling out your variables so that you're sure that you know what information you have. So a rigid cylinder is fitted with a movable piston. The cylinder contains a sample of helium gas. It has an initial volume of 0.125 and an initial pressure of 1 atmosphere. And the piston is pushed further into the cylinder. The temperature remains constant. So that literally means that I'm going to knock it out of the equation. Okay, the temperature is constant. The calculation, we want to calculate the volume. So V2 is X, and the new pressure is 1.5 atmospheres. All right, now when you set this up, you were instructed to first write the full gas law equation. All right, now since temperature is constant, I'm going to knock it out of the equation. And that's how I end up with what is essentially Boyle's law, which puts the two things across from each other. So one thing I noticed people doing when we were doing board work is that they were not using the formula to set themselves up. You have to check the formula before you start. If you just plug everything in as if you're always going to be multiplying these two terms and setting them equal to each other, you'll get it wrong. So now you can go ahead and plug in. I have to say, during these videos, I am trying to write on my screen without a stylus because my stylus is not working for some reason. So I do not want to go. I would ask you to put all your units, but um, I'm going to not do it because it's going to make my writing even messier. And also, it's going to make it a little bit less room. It's kind of hard for me to write small with my finger. Okay, so our second pressure is 1.5, and that's going to get it's going to be times X because you you don't know what the second volume is. So I'm going to go ahead and multiply this. So this is going to be 0.125 is equal to 1.5x because 1 times anything is 0.125, or you could put it in the calculator if that's how you want to do it. And now when I decide how I'm going to solve for x, please don't forget that these two terms are multiplied by each other. I'll do the dot because you guys seem to like that better. These two terms are multiplied by each other. They are not added or subtracted. And that is why when I go to get this x by itself, my goal is to get everybody away from the x. So I want to get everybody over to the other side. So I'm going to go ahead and divide both sides by 1.5. And I'm dividing because the opposite operation of multiplication is division. And then your x equals this should be 0.08, like about 0.083. So that makes sense. If I increase the pressure, it should decrease the volume, and 0.083 is a smaller number than 0.125. So even though that might seem like a weird looking decimal, try to get your number sense involved in trying to predict whether or not that makes your answer makes sense. If you understand the relationships in the gas law, the answer should make sense. All right, next type of question. We'll move down to number 2. Same idea. We're going to first get all our variables lined up. P1, V1, P2, V2, T1, T2, a light bulb, blah, 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 295 Kelvin is my temperature. Our pressure is 75 kilopascals. After 30 minutes, the temperature goes to 418 Kelvin, and the pressure of the gas inside the light bulb. What's the pressure of the gas? So I'm a little bit sloppy here. Sorry, guys. I'm not feeling well. So P is what I'm solving for. I'm solving for my second pressure. So I'm going to go ahead and get that set up in my formula. One thing you're going to see is that your volume is held constant, so you can knock your volume out of the equation this time. So when I go to write out the equation, this time it's volume I'm going to take out. And so this gives me a totally different equation. So make sure that that's what you're doing, because here you're going to have pressure over temperature. This is giving you Gay-Lussac's law. So I don't know why people thought they didn't need to do Gay-Lussac's law. Gay-Lussac's law is in the notes and it's in the chapter. It's just nice when you only memorize if you only work with the combined gas law equation, what you can do is do this trick where you just eliminate the variable that's being held constant, and it will give you the other laws. So you don't have to memorize the formulas for 3 different laws. It just saves you time, right? So I'm going to go ahead and plug in my pressure. My first temperature equals, I don't know what my second pressure is, and my second temperature is 418. And you can see that the setup here is very different. When you get it in this direction, what you're going to end up doing is you are cross an equal sign. This is not a conversion. So you are allowed to cross multiply. So you're going to go this way and then that way. Okay, so when you do that, you're going to get on this arrow, I'm going to call this arrow 1, 75 times 418 is equal to 295 times x. So let me just do the math really quickly in the background. Okay, so very quickly, let me show you the steps. I had 75 times 418. I did that first. That got me a very big number, 31,350. This is still equal to 295 times x. So now, in order to get x by itself, I wanted to get the 295 to move away from him. So since this is being multiplied, I divided both sides by 295, and I got 106.3 kPa. Okay, again, makes sense. My temperature went up, so my pressure went up significantly. My temperature nearly doubled, so it was, well, maybe not exactly, but it went up by about 100. So it's quite a bit. It's 295, so it was pretty high to begin with. All right, let's clear this and start the next one. All right, so now just to recap, we had an example where temperature was held constant, and we had an example where volume was held constant, and you saw that we were allowed to just take that out of the equation. So the next thing we're going to do is see if this one has all the variables or if we're still holding something constant. So a sample of oxygen gas in one container has a volume of 20 milliliters, so V1 20, at temperature 297 and pressure 101.3 kPa. All right, the sample is transferred to an entirely different container. This means that we're open to it having a new volume, right? Because the new container could be a different size. I have a new temperature here, a new temperature of 283. I have a new pressure here of 94.6. And after my question word, what, it says the new volume of the sample. That's what I have to find. So in this case, I cannot eliminate a variable. I'm actually going to use the full combined gas law this time. So I've got P1V1 over T1 equals P2V2 over T2. We're going to use the whole thing. So we're going to do 101.3 times 20 all over 297 equals X is my volume times my new pressure, which is 94.6, which is a little lower, the pressure, and my new temperature 283, which is slightly higher. So this might all even out. When you have a change like this where you can't tell if what's happening with the volume or the temperature or the pressure, if the variables are too many or changing at once, it will be harder for you to predict if it's going to go up or down, and then it's a little harder to check your answer. So even though the temperature went up, or sorry, went down, I might be expecting if the temperature goes down for there to be less pressure or for maybe the gas to not take up as much volume. The pressure also dropped. My pressure and my temperature dropped. So actually, I'm expecting that this is going to take up a little bit less volume. I don't know how much less. All right, so here's the order I'm going to do the math in because I'm going to pause the video so I can run it in the calculator, and when you get back, when I get back, everything will be written out for you. I'm going to first multiply these terms, and then I'm going to cross multiply them with these terms. And then I'm going to put that number here. Okay, then I'm going to go ahead and cross multiply these two numbers. And I'm going to keep my x. And I'm going to put that number here. And then that'll be equal to each other. And and then I'll decide what I'm going to do next. Okay, so here's what happened. I got some very enormous numbers here. When I did 101.3 times 20 and then times 283, I got 573,358. That's a big number. And then when I did 297, I went this way, 297 times 94.6. And then don't forget your x, so you know what you're solving for. I got 28,096. So then I divided both sides by 28,096 because I wanted this x by itself. So that 280, the 28,096 needed to go to the other side. So I divided both sides by 2,096. And I actually got not a very big volume change. It only changed by about a half a milliliter or 0.4 milliliters. And that kind of makes sense because it wasn't a very big change. Um, I dropped the temperature, but I also dropped the pressure. So that means that the volume didn't really change that much. And that's okay. All right, that was a harder one for you to kind of guess how how things would go based off of the variables you were given. Okay, next one. All right, now at this point on this particular quiz, um, I gave you credit for writing out all the variables and everything. So you got a point for writing it out, a point for changing the formula, so I could see that you understood you were leaving out a variable, if you were doing that, a point for plugging everything in with its units, and then a point for doing all your algebra correctly, and a point for getting the correct answer. So even though I'm not going to show you every single step necessarily on this last one, that was the way the quiz was graded. So you would have had to have done that if I had not handed it back to you as a self-graded quiz. So just keep that in mind. If you're doing the test and you see it says to show all your work, you have to show all your work. All right, so let's run through this one very quickly to keep the video from going too long. We've got a sample of gas at 330 Kelvin. So I'm going to put that as my first temperature. A pressure of 150 and a volume of 3.5 liters. And then on my other side, you have to be real careful about this. This is sneaky. First of all, volume is on the top of this equation. So volume 2 stays here. But what is my new pressure and my new temperature? Some of you will read this question and say, well, they didn't give me one. Yes, they did. They gave you standard temperature and pressure, and that will be on your reference table, right? So standard temperature is 273 Kelvin, and standard pressure is 101.3 kPa. If they do that to you and the problem is in atmospheres, you're going to use 1 atmosphere. You want to make sure all your units are correct. You can't use atmospheres and kilopascals in the same question. You have to use one or the other. So if this were a more complex question, you'd have to convert it. All right, so the math is going to go just like it did last time. We'll do the cross multiplication this way, and then the cross multiplication that way. Okay, so I went ahead and fast forwarded to how I did the cross multiplication. So I did 150 times 3.5 times 273. That got me this enormous number. Then that is set equal to when you cross multiply in the other direction. So this is your first one. And then there's your second one, 330 times 101.3 times my V2, my volume I'm solving for. Just really be careful. Don't drop your X because then you won't know what to do next. Now you will notice that there's a pattern here of every time we've been moving the stuff from the right to the left. That will not always be true. It will just depend on which side the X is on. So in this case, everything they've asked us to solve for is what happens in the second part. Remember, these are initial and final state questions. So if they were to ask you about something that happened in the initial state, you would need to make sure that you paid attention to the fact that that stuff was on the other side. Now, I don't know if there'll be a question like that on the test. I wasn't anticipating it, but just make sure that you're not making up fake rules for yourself, like, oh, you always move it from the right to the left. It will depend entirely on where the X is, where you move something in the algebra equation. So you just want to move it to the side where the X is not, so you can solve for the X. So where you move things will depend on what you're solving for. So after I divided both sides by 33,429, I got 4.29 liters. All right, let's move on. I'm going to pause the recording one more time to bring up, you guys wanted me to do a quick conversation about the vapor pressure graph. So I'm going to pause the recording to pull that up for you. Okay, now this reference table is table H. It is called the vapor pressure of 4 liquids. If you're not sure what vapor pressure means, you really need to go back through your notes and check to see if you went through the understanding for that. Vapor pressure is the pressure exerted on the surface of a liquid. Now, there's 2 ways you could think about it. You could think about it as the pressure exerted by some of the liquid that has already been evaporated into a vapor, pushing down on the surface of the liquid in the container, if that's in a sealed container. But it's sort of the same as the pressure at the surface of a liquid because the particles are trying to escape from a liquid state to a gas state. Okay. Essentially, what this graph is about is it's about the idea that if you have to escape, you want to go from being a liquid to a gas, you have to leave the liquid. So not only do you have to have enough energy to overcome the forces of attraction between the particles and escape, you also have to exert enough pressure to overcome the pressure pushing down on you. And that is why in this graph, there's a dotted line here showing you standard pressure. Because most of us at sea level, at least, are at standard pressure. That makes me wonder how they teach this class in like Colorado. But if you're at standard pressure, then this is the temperature at which the pressure on the surface of the liquid will be equal to the pressure of the particles trying to escape, and they'll actually be able to escape the liquid and go to the gas state, which is the boiling point of that liquid. The boiling point of a liquid is the temperature at which it actually starts to change from a liquid to a gas. And so when you're using this graph, if you know you're at standard pressure, all of these points are the point where the surface will the surface pressure will be equal to the vapor pressure, and so you will be able to boil. But you could do things at a different pressure. So that's the beauty of the graph. For each substance on this graph, you could look at it at a different pressure. So just be careful that you're sure what you're reading. You're reading pressure off the y-axis and you're reading temperature off of the x-axis. And what this whole air pressure versus boiling point thing means is that if you had less pressure pushing down on the liquid, things would be able to escape more easily. And so at lower pressures, you can actually decrease the temperature of the boiling point of a substance. Now, it's unusual because at extreme altitudes on Earth, you're not going to see the vapor pressure drop um, so much that the boiling point is going to be so different. You know, it might be 100 degrees Celsius at our pressure and maybe like 95 degrees Celsius at a really extreme high altitude. Um, you know, that's not that huge a difference probably, but you can do things in labs where you manipulate pressure by putting things in pressurized containers and dropping the pressure like creating a vacuum like we've been doing in class with our experiments. We created vacuums inside of jars with lighting a candle by sucking the air out of the jar. If you create a vacuum inside a container, you can lower the pressure in the container and force something to boil at a lower temperature. So that is something you can do in laboratory conditions. So this is some of the ways that we sort of manipulate the the properties of matter by changing the conditions that they're in. Um, all right, so just don't forget if you're reading this graph, each of these substances, the only thing I had to mark people wrong for last time you had a quiz on this was some people wrote that this was propane. This is not propane. This is propanone, which is a different chemical. It's in the same family as acetone, which is a nail polish remover. And propane is the stuff that goes in your grill that you burn. Um, it's a burnable fuel. They're not the same. Um, propanone and propane. So I have to mark you wrong because we are in the stage of um, putting, the names of chemicals mean something. So you can't confuse them because small differences can be a different chemical. The other ones are ethanol, water, and what is known as ethanoic acid. And that's basically how you read this graph. It's not very hard. You read the pressure off this side, you read the temperature off this side. The thing that actually threw people off the most about this graph is that the scales are not the same. So on this side, the scales are by fives, 5, 10, 15, 20, 25. And on this side, the scales are by tens, 10, 20, 30, 40, 50. And so that can throw people off. I had people give me incorrect answers because they were misreading the scales on the graph. And that's pretty much it. All right, I hope that's enough to help you guys to get ready for your test, which because I was not feeling well and I'm a little behind, that is why your stuff was not posted. So I am posting it right now.